Now that we have looked about how to plug these in algebraically, let's look at the graphs. All right, our exponential graphs, remember exponentials are in the form b to the x. The first one we're going to look at is our base is bigger than 1. If we're looking at our domain, remember domain is our x values. All over to the left, we have negative infinity. Over to the right, we have positive infinity. And notice with our graph, if we follow along, it has an arrow pointing to the left, which means it's going to keep going and going and going, which means we get to hit all the negative x values. So our domain, we're going to start with the smallest, which is negative infinity, because it'll keep going and going and going. Eventually, I'll be able to plug in negative 1,000, negative 1,000,000. On the flip side, going to the right-hand side, my graph keeps going up and up and up, and I know people are going to concentrate on that, but notice that it's going over. It's eventually going to hit all of our x values in the positives, because eventually I'm going to be able to plug in 1,000,000, a googolplex, which means that my domain is going up to infinity. And remember, the infinities both get parentheses. Our range is our y values. And remember, we're going smallest to largest. Right now, if we're looking at our y values starting low, there's nothing down below. But we start getting some y values, we start getting our graph above y equal to 0. Because if you notice, it's like there is a line keeping us from crossing along the x-axis. For that reason, we can get super close to 0, but we're not going to get to 0. So we're going to use a parenthesis. And then if we keep going up to find our highest y value, notice that it keeps going up, which means it'll go up and up and up and up and up, which means our range is going to go up to infinity. When we are looking at whether the graph is increasing or decreasing, you need to pay attention from left to right. From left to right, if we follow along our graph, we are going up. And if our graph goes left to right, going up, that means that our graph is increasing. Our x-intercept is where we cross the x-axis. Remember, our x-axis is down here, but we said that we were not going to cross or touch the x-axis, which means that our x-intercept does not exist. DNE does not exist. As for our y-intercept, remember y-intercept is where we cross the y-axis. So we're going to scan along the y-axis and see where we cross. We do cross at that ordered pair, which means that we have a y-intercept of 0, 1. And finally, our horizontal asymptote. Your horizontal asymptote is an imaginary line that your graph gets as close as it can to without crossing. It's restricting our graph from going any higher or lower. We said we could not go beneath the x-axis where y is equal to 0. which means that our horizontal asymptote is y equal to 0. Remember that these are for the parent functions. We haven't made anything that looks like our examples previously where we were plugging in where 5 times 2 to the 3x plus 4. We're doing nice and straightforward b to the x. So some base raised to the exponent, nothing added or subtracted in the exponent or after. Next, we're looking at our graph where our base is between 0 and 1. So we have some fraction, but it's positive. If we're looking at our domain, remember domain is our x values. We have negative infinity to the left, positive infinity to the right. Our graph will keep going and going and going to the left. That's why the arrow is there, which means eventually we're going to head off into negative infinity going to the left. If we look at our graph to the right, it keeps going and going and going. And it'll continue to go and go and go because that arrow is there, which means that our highest part of our domain is positive infinity. With our range, remember that those are our y values. And here our range, looking at our smallest y value, because we're going up and down, we try to get down past the x-axis, but it's just not working for us. Again, we have a line that is in our way. We cannot get below y equal to 0. So our range is going to be 0 with a parenthesis because we can't hit 0. Let's go for the highest. If we try to follow our graph to see what our highest y value is, it skyrockets up to the left, which means we're going to hit all of those positive y values eventually, which means our range goes from 0 to infinity, parentheses around both. Remember, when you're doing increasing and decreasing, we read from left to right. From left to right, if we follow our function, we are going down. Since our function goes down from left to right, our function is decreasing. For an x-intercept, remember x-intercept is where we cross the x-axis, but we said we weren't going to be able to cross the x-axis. We couldn't get over that y equal to 0 line. So again, our x-intercept does not exist. Our y-intercept, where we cross the y-axis, so again, scroll along the y-axis, notice that we cross at that ordered pair that I just circled. We cross there, which is the ordered pair 0, 1. Our horizontal asymptote is that horizontal line we just can't seem to cross. And remember, we keep that as a dashed line. And if we cannot cross over that y equal to 0, that means we have a horizontal asymptote of y equal to 0. Now, I know you may be wondering, is your horizontal asymptote ever not 0? Yes. So, bonus example. Let's say we have f of x equal to 5. No, I've used 5 so many times. Let's try something else. 7 to the x plus 1 plus 121. This guy is an exponential. because our variable is in the exponent, which means that our domain is negative infinity to positive infinity. But this time, our horizontal asymptote is not 0, because we have a couple other things going on in this example that we didn't in the previous. But if we look at our previous graphs, they had y equal to 0. Our horizontal asymptotes are going to come from whatever follows our function. So if we have f of x equals b to the x, there's nothing at the end here. It's automatically a plus 0 if we want to put something in. If I look at the second case, I still have b to the x, nothing after it, which means I could put in a plus 0. Whatever we add or subtract at the end is going to be our horizontal asymptote. So here in this problem, we're adding 121, which means that my horizontal asymptote is going to be y equal to 121. It's always in the form y equal to. Let's try another one. Let's say I have g of x is equal to 15 to the 2/3 x plus 11 minus 72, just for a heck of it. This guy, although he is ugly, he is pretty ugly, he is an exponential. And that's because our variable is in the exponent. That means our domain is immediately negative infinity to positive infinity. And if we're looking for our horizontal asymptote, we need to look what we're adding or subtracting after the base, after the exponential piece. So our horizontal asymptote in this example, we're going to have y is equal to negative 72. Let's put this all together and see how it goes when we graph it ourselves. Okay. So we have example number 3. It is an exponential because the variable is in the exponent. Because it is an exponential function, we know that the domain is immediately negative infinity to positive infinity. With the horizontal asymptote, we have f of x equal to 2 to the x plus 1, but the x plus 1 is in the exponent. There's nothing after. So let's go ahead and put a plus 0 because our horizontal asymptote is whatever is added or subtracted at the end, which means that our horizontal asymptote is y equals 0. To find your y-intercept, we need to plug in x equal to 0 because a y-intercept is always in the form 0, comma, some number, which is why we had 0, 1 in our previous two examples. Here, if we plug in 0, I'm going to have 2 to the 0 plus 1, because x plus 1, which gets me 2 to the 1, which gets me 2. So the y-intercept we just found is the ordered pair 0, comma 2. We need to find 3 additional ordered pairs with at least one of them being negative. I'm going to write down our function again. We had f of x equal to 2 to the x plus 1. We need 3 additional ordered pairs. You can do any x value you want, but one of them needs to be negative. I'm going to do an XY chart. Now remember, exponentials are going to get really big very quickly. So when you're plugging in values, you probably don't want to do x equal to 7, because then we would have 7 plus 1, which is 2 to the 8th. 2 to the 8th gets us 256, and nobody wants to have to graph that by hand. So let's stick to the lower values. We already have 0, so let's do x equal to 1. Let's try x equal to 2. You could do 3 if you wanted. And we need a negative x value, so let's do -1. For x equal to 1, yes, you need to be able to show this work. We would have 2 to the 1, plugging in for x, plus 1, which is 2 squared, which gets us 4. We just found the ordered pair, 1, 4. For x equal to 2, we would have 2 to the 2 plus 1, plugging the 2 in for the x, which is 2 cubed. Remember that 2 cubed is not 2 times 3. It's 2 times 2 times 2, which gets us 8. So we just found the ordered pair, 2, 8. And then the last one, we have x equal -1. Plugging in, we'll have 2 to the -1 plus 1, which gets us 2 to the 0, which gets us 1. So our ordered pair is -1, 1. And just to prove a point, I'm going to have one more example. I'm going to squeeze in a -3, just so you can see what happens when you get more negative. Okay. We would have 2 to the -3 plus 1, which gets us 2 to the -2. If you use your calculator, that gets you 1/4. So we start getting small very quickly. I'm going to go a little bit out of order because I know a bunch of you are visual, so this is going to help you with determining your range and increasing and decreasing of your function. So in our example, we already have the coordinate plane, so we don't need to draw our x and y axes, but we do need to start plotting our points. We have the point 1, 4, so 1 to the right, 4 up. That's the ordered pair 1, 4. We have our ordered pair 2, 8. So over 2, up 8. We have our y-intercept that I skipped because it wasn't in the chart, which was 0, 2. We had the ordered pair -1, 1. Here, I'll do it up here. And then we have the ordered pair of -3, 1/4. So a little bit above the x-axis. We have a horizontal asymptote of y equal to 0, which means I'm going to have a dashed line along my x-axis. I'm going to go ahead and label it. And now I get to connect the dots for my graph. Starting at -3, 1/4 and going to the right, I can connect them in a pretty nice fashion going up. To the left, I'm going to get as close to the horizontal asymptote as I can without crossing it. So looking at that graph, our range for our exponentials is always in the form either our horizontal asymptote, infinity, or -infinity to our horizontal asymptote. Okay. If our function is staying above the horizontal asymptote, which we are here. The horizontal asymptote is our base. When it's our base or our bottom, we're going to have the first case. If it is our ceiling or the top, we're going to have the second case. So ours falls into the first case, which means that our range is going to be 0, infinity. If you're having issues writing your infinities, don't worry, mine never look very good. If you need to, draw 2 little circles next to each other. And we saw when we were plugging in more positive values for x, we got bigger and bigger values for y. When we went from left to right, graph goes up. And because the graph goes up, our function is increasing. You need to be able to explain how you know it is increasing or decreasing. And we already graphed the function, including the asymptote.